Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 41, and it is entitled Two-Body Tension Problems with Friction. I want you to cast your mind back to Lesson 35, when we had two blocks that were strung together with a string, and they are accelerating, such as maybe two blocks with one of them on a horizontal surface, or maybe two blocks with one of them on an incline. Here are a couple of diagrams to remind you of what we're talking about. Our job was, when these surfaces were without friction, to be able to determine what the tension in the string was and what the acceleration of the system was. And you'll remember that we approached these problems with a certain set of techniques in order to solve them. We are now going to add friction. And I would suggest that our approach is still going to be the same. We just have another force that we have to deal with. They seem a little bit more complex because friction's involved, and we'll still have some decisions that we need to make. But the idea that we're going to take to approach these problems is going to be the same. So let's remind ourselves of what that approach was. The first thing we did was we sketched a free body diagram for each object. The next thing we did was we determined if there was going to be any acceleration, and if there were, then which direction that acceleration would be. And we would choose the direction of acceleration to be the positive direction. Finally, we then wrote Newton's second law for each mass, and then we solved the system of equations that we had for the things that we were looking for, which is usually the string tension and the acceleration. We're going to take this same approach, but now we're going to add a force, and the force that we're going to add is the frictional force. So the frictional force is going to appear in the free body diagram, and it will also appear in Newton's second law. The best way to illustrate this is to actually work through a couple of examples. So let's take a look. Here's the first one. The coefficient of kinetic friction between the block and the table is 0.80. The 3 kilogram block is connected to the 5 kilogram block by a rope passing over a massless, frictionless pulley. The system is released from rest. Find the acceleration of the blocks and the tension in the rope. Let's begin by sketching a free body diagram for each of the objects. Let's begin with the object that's on the table. This black dot represents the 3 kilogram mass. There are four forces acting. There's the string, which pulls the mass to the right. We're going to call that the tension force. There is the earth, which pulls the mass downward. We'll call that the weight. There's the table, which pushes the mass upward. We'll call that the normal force. And there is the surface of the table interacting with the bottom of the block that tends to push the block to the left in the opposite direction of the motion. It's obvious that the direction of this acceleration, if there is any, is going to be to the right on this block. And so we're going to call the right positive. We can write some expression for each of these forces. For instance, I know that the weight of this 3 kilogram mass is going to be m times g, and the frictional force is going to be mu times the normal force. Let me include that in this free body diagram. Let's sketch a free body diagram for the 5 kilogram mass. There are two forces acting on the 5 kilogram mass. The string pulls the 5 kilogram mass upward, and the earth pulls the 5 kilogram mass downward. Now, some people at this point might be tempted to say, oh, well, it's obvious that the string tension must be 50 newtons because it's going to be equal to the weight of the 5 kilogram mass. That's not true, and the reason it's not true is because if the 5 kilogram mass is accelerating, then the string tension cannot be the same number in the opposite direction as the weight. So I know the string tension is going to be something less than 50 newtons, but I don't know what it is. That's one of the things I'm looking for. All right, that's the first step. We've sketched our free body diagram. The next step is to determine if the system accelerates, and if so, in which direction it accelerates. Now, they wouldn't be asking us to find the acceleration if there were no motion. And so I'm going to make the assumption that there is acceleration here. You may have to find if there is a coefficient of static friction in place, whether or not that you would get any motion when you release the system from rest. Because it may be true that static friction is sufficient to hold the system in place, so there would not be any motion. But in this problem, they don't give us anything about static friction, and so I'm going to make the assumption that the system does accelerate. The 5 kilogram mass is going to descend, the 3 kilogram mass is going to accelerate to the right. So now I want to write Newton's second law for each of the objects. Let's start with the 5 kilogram mass. Newton's second law says the acceleration of the 5 kilogram mass is equal to the net force acting on the 5 kilogram mass divided by its mass. Since downward is the positive direction, the net force is going to be the weight of the 5 kilogram mass minus the string tension. And since the weight is equal to m times g, then I can substitute that in, and I will have an equation for the acceleration of the 5 kilogram mass. Now let's work on the 3 kilogram mass. The right is positive, and so we can write Newton's second law for that mass. The net force is equal to the string tension minus the frictional force. Now I want to make some substitutions in here. The frictional force is equal to mu times the normal force, but in looking at my free body diagram, I can see that the normal force is going to be equal to the weight. So the normal force is going to be equal to m3 times g. Okay? So now I have two equations and two unknowns. The blue equation came from the 5 kilogram mass. The green equation came from the 3 kilogram mass. And what I claim is I know everything in those equations except Ft and A. Those are the things that I want to look for. Now at this point, you could throw in numbers in your TI solve and solve this equation, this system of equations. I'm actually going to solve the system algebraically. So I'm going to roll up my mathematical sleeves and get to work. Since both of these equations have A in them, I'm going to set the right-hand side of the blue equation equal to the left-hand side of the green equation. Now the only thing I don't know is Ft. So I'm going to cross multiply and then massage this equation until I can get Ft on one side and everything else on the other side. I'm going to gather the Ft terms on the left-hand side, and I'm going to put the Ft terms on the right-hand side and put everything else on the left-hand side. Now I'm going to factor common things on both sides, finally get Ft by itself, and there's an expression for Ft. Now I'm going to throw in the numbers, and now I'll substitute those numbers into the calculator, and I get that the string tension is just under 34 newtons. Now I want to figure out what the acceleration is, and it doesn't matter which equation that I plug it back into, but I'm going to take this string tension and put it into the first acceleration equation and solve for what the acceleration is. And now I'll put it into my calculator, and I find that the acceleration is 3.25 meters per second squared.